Today we're going to look at stoichiometry. So let's just look at the word itself. Stoichio comes from a Latin word and it means element. The metry section, like geometry, trigonometry, all of those ones, means to measure. Okay, so like trigonometry, the metry means measure, trigon means the triangle. So trigonometry are all about triangles. So stoichiometry is all about measuring the elements. And the type of questions we'll get with this chapter is measuring specific percentages of elements within a compound. And we'll look at that throughout this video. So the first little section that we're going to look at is this question. So ammonium nitrate, NH4NO3, is used in fertilizers. Calculate the percentage nitrogen in the compound mentioned. So we need to figure out of this whole compound, how much of it is made up of nitrogen. So to do that, we need to compare the nitrogen, the amount of nitrogen, against the amount in the whole molecule. And we'll do that by mass. So I'm going to write out the relative molecular mass of the whole compound first of all. So we have a nitrogen, which has a relative atomic mass of 14. We have 4 hydrogens, each having a relative atomic mass of 1. Another nitrogen, and 3 oxygens, which have a relative atomic mass of 16. And if you add that all up together, you're going to get the relative molecular mass of the whole compound, ammonium nitrate, to be 80. Now the mass of nitrogen, the element that we're interested in, we have 2 of them, so 14 plus 14 gives us 28. If we compare the amount of nitrogen against the amount, or against the whole compound, we will see the amount of nitrogen present in the compound. To do that, you put them as a fraction. So 28 is representing the nitrogen, and 80 represents the full compound. So you're seeing how much of the nitrogen is in comparison to the full compound. And 28 over 80 will give you a fraction. So it's asking for a percentage. All you have to do is multiply it by 100 and you're going to get 35%. So that means that 35% of the ammonium nitrate is made up of nitrogen. Okay, so I'm going to write out another one for you. And then you can pause it once you see that when I read through the question and give it a go yourselves. Okay, so here's the question. Calculate the percentage water crystallization in the magnesium sulfate crystal. And you see that the 7H2O here. So when you're doing out the calculations, you'll find out the relative molecular mass of the whole thing and compare the 7 water molecules against the whole substance there. Okay, so you can pause now if you want to try and do it. Okay, so again, we're going to look at the relative molecular mass of the whole substance. So the relative atomic mass of magnesium is 24. We have sulfur, 32. 4 oxygens. And then the 7 goes into the whole water molecule there. So 7 H2s. So that means 14 H's. 7 by 2 is 14. And then 7 by 1 oxygen means 7 oxygens. So 7 by 16. So once you add all those up, you get the relative molecular mass of that whole compound here. And it's going to be 246. We want to compare the water crystallization, so the 7H2O section. So if I take that and find out the relative molecular mass of just the water section, it's going to have 14 hydrogens, each have an atomic mass of 1, and 7 oxygens. Okay, so then we can again just compare this number against this number. And we can find out the percentage water that's present in that molecule. Percentage, just need to multiply it by the 100 there to convert the fraction into a percentage. And you'll get 51.2%, which means that in this compound here, which is Epsom salt, the magnesium sulfate with the water of crystallization attached, there is 51.2% water present. Okay, so now we're going to look at the empirical formula and the molecular formula. Okay, so again, stoichiometry is all about calculating how much of an element is in a certain compound or molecule. So there's two different types of formulas, molecular formula and the empirical formula. So I'm just going to go through some examples first, and hopefully as I go through them you might catch on what the difference is between them. So on the left hand side I have the empirical formula here. And then the molecular formula is here. So the difference between those two, hopefully you can see, is that the molecular formula has a higher number associated with each element. See how C2H4 and the C has just a 1 and the H is a 2. So on this side, the numbers are actually higher than the empirical formula. But also, the thing is that's the difference between empirical formula and the molecular formula is the empirical formula is like the smallest ratio of the molecular formula. So you see how we've got 2 carbons and 4 hydrogens? That's a 2:4 ratio. So for each carbon, there's 2 hydrogens. So if you broke that down 2:4 to the smallest ratio, dividing both sides by 2, because 2 goes into 2, 2 goes into 4, it will become a 1:2 ratio, which is why we have C1, only one of them, and H2. So the empirical formula is just the molecular formula, but in the smallest ratio possible. So let's take a look at this molecular formula. Try and see what the empirical formula would be. So it's a 2 hydrogens, 2 oxygens, a 2:2 ratio. What number goes into both of those? And you can whittle it down to a 1:1 ratio. So the empirical formula would be literally HO. For each hydrogen, there's 1 oxygen. Okay, let's give another one. So we're going to go with CH2O, and the molecular formula, let's say for example, is C6H12O6. Breaking that down, 6, 12, 6. 6 can go into all of those numbers and it becomes 1, 2, 1, which is what we have right there. C4H12O2. See if you can work out what the empirical formula for that one is. So 4, 12, 2, what number can go into all of those? It's a 2, so we can get the empirical formula to be C2H6O. Okay, and you notice that the molecular formula is nearly always bigger than the empirical formula. They can be the exact same. Let's say if this was the actual ratio and that was the molecule, that could be the molecular formula and the empirical formula. Okay, so just to summarize, I'm going to write a few notes on those two. So let's go for the molecular. The molecular is the actual number of atoms present in the molecule. So if you were to draw this one out, you would need to draw 4 carbons, 12 hydrogens, and 2 oxygens, because that's what's actually present within the molecule. The empirical is just showing you the ratio of atoms present. It means that for each 2 carbons present, there's 6 hydrogens and 1 oxygen. For here, each hydrogen has 1 oxygen, which is the same thing here, okay? So the molecular formula is what we would use in balancing equations and working out percentages, because that's the actual molecule that is present. The empirical just gives you the ratio within the molecule. To switch between both of them, there is this formula. The empirical times a certain number n, which gives you the molecular. Okay, so let's look up here at the examples that we've just seen and try and find out what n is for these guys. So going from this over to this one, what did we have to multiply carbon and hydrogen by? Carbon's going from 1 to a 2, and hydrogen's going from a 2 to a 4. So n would be 2 in this case. Again, n is 2. Here, think about what n is going to be here. N is 6 because you're multiplying C times 6. 2 times 6 is 12, and the 1 times 6 is 6. And then going from here to here, n is equal to 2. Okay, so this is a very important little formula to remember, because we're going to be using it in a question now that I'm going to write out for you. Okay, here's the question. An acid taken from rhubarb contains 26.7% carbon, 2.2% hydrogen, and 71.1% oxygen by mass. The relative molecular mass of the acid was found to be 90. Calculate the molecular formula. Okay, so I have 3 percentages. And then I have the relative molecular mass of the compound. So what I'm going to do is I'm going to work with those percentages first, but it's by mass, so I can just convert those percentages straight into mass and pretend that we have a 100-gram sample, just like 100%. So if I pretend that I have a 100-gram sample, all the percentages will turn and convert into grams. So let's just write down the elements. Carbon, if it was a 100-gram sample, 26.7% of it would turn into 26.7 grams, and so on for the rest of them. Okay, so now I have the mass of each of the elements, and if I have a mass of a certain element, I can find out how many moles of that element I have. And I do that by dividing each of those masses by the relative atomic mass of the element. And you can find those relative atomic masses in your periodic table. And that will give me the number of moles for each section. So we usually convert straight to moles because we measure elements in moles usually. Moles are a preferred measurement in chemistry. So usually when you have mass, you'd go straight into moles. So it seems I've around the same amount of moles of carbon and hydrogen reacting together, but I have more oxygen. So I'm going to try and find a ratio now of those numbers. So I'm going to go over here and see ratio. So to get the ratio, I'm just going to divide all of the numbers by the smallest one. And what I mean by that is, let's say you had a 4:2 ratio over here. What you do to find the smallest ratio is take the smallest number, which is 2, and divide it in. So what's 4 divided by 2? 2. What's 2 divided by 2? 1. So doing that gives you the simplest ratio possible. So the smallest number here is the 2.2. So 2.22 divided by 2.2. And you're just going to take all of them. And that works out to be near enough to 1. So I'm just going to round it to 1. 1 here again. And a 2. So I'm left with whole numbers. What that tells me then is that for every carbon, there's 1 hydrogen and 2 oxygens. So it's telling me the empirical formula. This ratio at the very end of all that calculations tells you the empirical formula. Only it's telling you how the elements combine in terms of its ratios. So if I was to write that out now, the empirical is C1H1O2. That's the empirical formula. Now it asked me to calculate the molecular formula. I do have a little formula to go by. Remember, empirical formula times N gives me the molecular formula. I don't know what N is, and I don't know what the molecular formula is. So I'm going to write in CHO2 times a certain number is going to get me my molecular formula. Now what you want to ask yourself is, do I know anything about the actual final molecule? I know its relative molecular mass, don't I? It's 90 right there. So I'm going to convert this formula into a mass. So I know that the molecule I'm dealing with has a relative molecular mass of 90. So I'm going to put 90 in for there. Don't know what N is. And I can find out what the relative molecular mass of this little thing here is, the empirical side of it, by going 12 for carbon, 1 for hydrogen, and 2 times 16 for the oxygen. That's going to get me 45 for that, times N is 90. So with a bit of manoeuvring, I can find out what that number N is, which is 2. So that means I'm going to have to multiply the empirical formula by 2 to get what my molecular formula is going to be. C2H2O4. And that is the molecular formula. So I'm going to write up one more question for you. And then the next question is going to be a water of crystallization one. So it's going to be a tiny bit different, but hopefully you can get the same steps out. Okay, so we have washing soda that was analysed and found to have the following composition: carbon 4.2%, oxygen 16.8%, sodium 16.1%, and water of crystallization 62.9%. So if we do out the elements that we have to deal with, we have carbon, oxygen, sodium, and the water of crystallization is going to be H2O. So you keep the H2O together. You treat water of crystallization as one element by itself. Remember, so if it's a percentage and we have a sample of it, we can convert it straight to mass. If we're assuming the sample has 100 grams of it, all of those percentages can turn straight into grams. And we know we measure things using moles. So again, work out mass divided by the relative atomic mass of these elements is going to get you the number of moles of that element present. And then for the water, it is the 2 times the hydrogen plus 16 for oxygen. And then we can work out all of the moles. I'm rounding there for the 16.8. And 3.5, we round up as well. Okay, so then we know we have to do the ratio. We want to find the ratio for the empirical formula. And the moles is giving a ratio already, it's just not in its simplest format. So to get the simplest format, you divide all of these numbers by the smallest one, which is 0.35. And hopefully that will get us closer. See, that's 1. 1 divided by 0.35 is going to give us 2.85. 0.7 divided by it. Okay. So even though this one is not fully there, the rest of them are, so that's okay. So we're going to round that up to 3. So remember, this gives us the empirical formula, the ratios. C1, sodium, 2, C1, oxygen, 3, dot, so water crystallization, so the dot goes there. And then we have the 10 waters. So there's your empirical formula for that. Now, if it was asking for the molecular formula, it will give you the relative molecular mass. And you'll need to figure out, what do I need to multiply this whole compound by, what number, to get the molecular mass. Okay, that's that for this video.